geometry, which is going to be limiting reactants and excess reactants. And then we're going to move into some solution calculations, which is 3.7. This molarity, this should all be review of last year as well. All right, so reviewing limiting and excess, that's going to be the first part of this set of notes and example problems. But before we start looking at our example problems, let's go back over our learning targets. 4.5, enduring understanding, still looking at the law of conservation of mass there as to why stoichiometry works. But today, after this, you should be able to identify a limiting reactant and an excess, but if you can identify the limiting, you can identify the excess as well, and calculate how much of the excess remains. All right, what is a limiting reactant? A reactant in a chemical reaction that limits the amount of the product that can be formed. So the reaction is going to stop when all of the limiting reactant is used up. And it determines the amount of product. Now remember, the amount of product, this is going to be your theoretical yield. That part that we put on the bottom of the percent yield equation, that's going to be your theoretical yield. And you're going to be able to determine that from your limiting reactant problems. So let's take a look at this analogy example. Real quickly, which is limiting the number of cars that can be made? Is it the car bodies or the tires here? Definitely the car bodies. Very good. As you see over here, it tells us there's 16 extra tires. So that means they're in excess, obviously. So we would label this one the limiting reactant. This one would be the excess reactant. So the car bodies there. Very good. All right, the excess reactant, the reactant in a chemical reaction that remains when the reaction stops after the limiting reactant is completely consumed. Now we like to use this word in reactions: consume, produce, those kind of words. You'll see them in the AP questions. Also added to make sure that the other reactant is completely used up. You add an excess reactant to make sure that the other one is no longer there. And the excess reactant remains because there's nothing that it can react with. So it's just there by itself, still floating around in the flask or the beaker. So let's look at this example. This is what we call a particulate model diagram, reactants and products, where they're using the little, circle diagrams. You saw these last year or the year, before if you were a senior. You saw them in Chemistry 1. They like to use them on the AP exam. They use them all throughout the curriculum, so we're going to have to get used to reading these particulate model diagrams. So the reaction right here is sodium plus chlorine giving you sodium chloride. And if we're remembering and looking correctly at our stuff here, these ones that have the double circles that are in green, which reactant do you think they represent? Yeah. That's going to represent your chlorine, because remember, the chlorine is a diatomic molecule, so it exists as the twin molecules where they have, the covalent bond here. Elemental diatomics, Dr. Brinkelhoff, the bromine, the iodine, the nitrogen, chlorine, hydrogen, oxygen, and fluorine. These all exist as diatomic, remember. So this is going to be your Cl2. That means that these singular red circles must be the sodiums. Okay, now this is before on this side. Here's the products over here. If you're looking at what happens afterwards, which is the excess reactant in the picture above? As you can see, there's 2 extras of the chlorines that didn't get incorporated into the ionic compound's lattice structure. So remember, this is negative. These ones are positive, negative, positive. That's how the alternating charges go in a lattice crystal of an ionic compound. But these ones are extra. They're left over. So obviously the chlorine is the excess reactant. That means the sodium has to be the what? The limiting. Good. So that's your reactant. Very good. Now let's do another example. Now that you kind of have the idea of what a particulate model diagram looks like, try this one. See what you come up with here. For the reaction of the diagram, which is the limiting, which is the excess. We have hydrogen plus oxygen giving us water. It's quite a good diagram here. Yeah, as you can see here, they identify the red circles here as oxygen and the white circles, those are the hydrogens. Over here, everybody knows the Mickey Mouse ones as the water, right? So looking at our product before and after, you see that we do still have some oxygens floating around. So yes, oxygen is the excess. And do we see any of the double white ones? No, they're all gone. So that must be hydrogen is the limiting in this case. Okay, so far so good. All right. Now let's talk about calculating. For each reaction, calculate the amount of product formed. The smaller the answer indicates the limiting reactant and the amount of product formed, the theoretical yield. So when you work the problems, you're going to calculate them, and then you have to look for the smaller amount to determine the other parts. Looking at this example, which is starting out with very basic stoichiometry stuff, we have carbon monoxide reacting with oxygen to give us carbon dioxide. How many moles of carbon dioxide will be produced if we have 15.8 moles of CO and 9.75 moles of oxygen? Now, what you need to recognize here, as you can see, is they gave us amounts for both reactants, and that's the quickest, easiest way to remember that this is a limiting reactant problem, because they gave us amounts for both. If they only gave you an amount for one, they'd say the other one is in excess. And then you only have one T-chart to do. But when you have both reactants here, that means you always have to do at least 2 T-charts. So these problems are a little bit longer and they have more length to them. And I need to know the moles of the carbon dioxide. That's what I'm looking for here. So we're going to go ahead and set this up. And go ahead, I'm going to go back to orange because it's better to see. So 15.8 moles of CO. Now when I'm going from CO over here to CO2, and I'm starting with moles, what step do I need to go to right now? Yes, it's the mole ratio step. So moles of CO goes down here to the moles of carbon dioxide on top. This is a 2, this is a 2, so it's 2 to 2. That's an easy calculation. Moles of CO cancel, and then the 2's cancel, so really I just have 15.8 moles of CO2. That's from my first reactant. Done the first reactant. Now I'm going to do the second reactant and compare the answers. So this is moles of oxygen. Also just a mole ratio because it's mole to mole. So we do moles of oxygen going to the moles of CO2 here. Now in this case, we still have the 2 for the CO2, but the oxygen doesn't have a coefficient, so that's an understood 1. So we're going to put that here. Multiply the 2, right? And I believe you get 19.5 moles of CO2. But please check on your calculator. I make mistakes when I punch in numbers too, so sometimes I get the wrong answer. Sounds good, thank you. All right, now out of these two, which one happens to be, okay, that's not working. Erase that. No, right click, right click. Come on, right click. I swear I don't know how to make this work, but okay. And it keeps going back and forth from 10 mode. Sorry. All right, I give up. I guess we're staying with this color. Okay. Which one came out less? Obviously this one right here. Okay. That one came out less. So this is our theoretical yield. So that's going to be this amount of moles produced. And then, yes, over here, that identifies the CO as the limiting reactant. That means the O2 is got to be the excess reactant. Very good, very good. All right, look. All right, we did that right. Good. Now, that one was simple because it was all mole to mole, only one step. Now we have to go to the grams stuff. We have grams now. This is going to be 55.00 grams. This one's 80. Now they're mixed together and they react according to the equation above. What is the maximum mass of water? So we need mass of water here. The mass of water. Forgot my G here. All right. Now you can set this up multiple ways. I'm going to set it up and work it to moles, and you're going to figure out why I do this later. But and then just once I get the lower mole amount, I'm going to change that one to grams. You can work them both to grams if you want to. That's fine. That also works. But sometimes you also later on in a free response problem need the moles. So that's why it's nice to work it to moles. Okay, so here are my two reactants. I got to figure out which one's going to run out first. I have dinitrogen tetrahydride and I have dinitrogen tetroxide. And we're working it over here to water. So both water. Sure, go ahead.
I don't know if it's because my notes printed out wrong, but my thing only, my value is 55.0 instead of 55.00.
Oh, it's fine. It just means I added on an extra significant figure. So you can definitely just add it on. I must have not re-edited it afterwards, deciding that I wanted 4 significant figures. Okay, good. All right, so first thing I need to do in order to get over to water, though, is I need to get rid of these grams. So I'm going to diagonal those down and go to 1 mole and to H4. And molar mass off the periodic table, nitrogen's 14.01. There's 2 of them, multiply that by 2. Hydrogen's 1.01 times 4, so that's 4.04. I add that in. I end up getting 32.06. So far, so good? Does your molar mass agree with my molar mass? All right, good. Now we're going to switch to the compounds. We're going to get rid of this compound and go to the water. So moles of N2H4 go down here. Moles of H2O on the top. So this is going to be 4. This is going to be 2. Sorry, 2, because this is a 2 here. And now we switched compounds. Good. So I'm going to stop here. Like I said, I go to moles first. And calculate that. So multiply 55 times 4, divide it by the 3206, and then hit enter, divide by 2, and I think you get this number. Did you get that number? Yep, all right, sounds good. Now we're going to look at the other reactant, figure out and compare the moles of water. So here I still diagonaling down the grams so I can go to moles of the dinitrogen tetroxide. Yes, we're going to get there, don't worry. I always go to moles first, and I'm going to show you why. So 1 mole here, 2 nitrogens at 14.01. Plus 4 times the 16 gives us 64. So add that up. This should be 92.02. Did you get that? All right. And then mole ratio here, switching over to water from the dinitrogen tetroxide. And we have 4 moles. This time it's to 1 mole because this is a 1 here. All right, and if I'm not mistaken, the mole amount, when you multiply 80 times 4 divided by 92.02, you get 3.478 moles of water. So far, so good. Now, which one is less amount? Or which one is the least amount? yeah, so that's going to be our limiting reactant. We're going to go with that one for our limiting reactant. This one is the theoretical yield, and this one is our limiting reactant. So that means this one must be our excess reactant. Now, to see here, it's working better now. I'm getting a handle on it. Let's go for the red. All right. So at this point, I still need grams. You're right. So I'm going to finish it out and change this one over to grams here. So 1 mole of water is 18.02 grams of water. Does everybody remember that one from last year? We had to do that one so many times. We had it memorized. When you multiply this out, I know, right? Water's easy to remember. You end up getting 61 point, I think it's 83 grams of water. Is that what you got? Yes, no? Okay. So, like I said, the reason why I go to moles first and then only change the one over at the end is because sometimes in these free response problems, you will have, in these free response problems, it will ask for moles of certain things. And if you have it already changed over to moles, it's a lot, you have, it's quicker and it's faster. So you can change them both to grams if you want to, though, and go from there. This is just, I always stop at the mole and then go on, because I've noticed over the 5 years that I've been teaching AP that they ask a lot of stuff about mole questions, and this makes it go faster. Yes, go ahead.
So for using significant digits, so after we did the first one with the N2H4 and we got 3.431, so we should just use significant digits as soon as we get the value. Like, we don't use significant digits only on the end value. So like the whole process in between, we're using significant digits. Because like I would have thought that when we got 3.431, we should have put like the entire number and try and be as specific as possible, and then use significant digits at the end. That makes sense.
And yeah, and you can do it that, like, yeah, no, I just wrote down 4 numbers there, but I usually just keep it in my calculator and then keep going.
Okay, so like you do use the whole thing though.
Yeah, you want to do it, yeah, till you get to the end of the calculation. You want to round at the end of the calculation. Very good question. But yeah, so I don't know if you can see, but I kept it in my calculator, and then I go and I keep going. But I wrote it down there so I could show my work of how I'm setting it up. I'm just, yeah, I wrote this down here so I could set up the next T-chart so I could demonstrate the work, because on the AP exam too, you need to be able to show your work and where you're going from it. I don't think that they really care if you round in between. You might be off like by a 10th or something, or a 100th or something. They're not going to care that much about it, but you know, you technically are supposed to wait till the end to do the official rounding. So good question. All right, now let's take a look at the excess part. We figured out the limiting, we figured out the excess, we figured out the theoretical yield in moles and grams, but now we need to know how much of the excess is left over. Good. All right. Now there's 2 ways to do this, and you can decide whichever way you want to. It's fine with me, but, and I'm going to start picking up the pace here, but how much is left over the excess reactant? We know that the excess reactant was this one, right? It's the N2O4. All right, so if you're going to calculate using the limiting reactant, you work it to the excess reactant, basically, is what you do. So I'm going to start with my limiting, which is 55.00 grams of the N2H4. And I'm going to work it all the way to grams of my N2O4. So remember, this one was 32.06 grams, N2H4, 454. The limiting one, remember, this was the limiting reactant. So I'm starting with the limiting reactant amount, which we started with 55 grams. That's where I'm starting there. Yes. So that equals 1 mole of N2H4. Now I'm going to use mole ratio to switch between the two. So 2 moles N2H4 equals 1 mole N2O4. And then I'm going to go to grams. So 1 mole N2O4. And this is going to be 92.02 grams. Yes, the smaller value from the previous slide where we decided that the water amount was smaller, that was going to tell us what was the limiting reactant. Okay, so looking here, you calculate this, and I think you get 78.93, but go ahead and check me. Grams of N2O4. If you're doing this method, you would solve for this. This is the used in the reaction amount. That's how many grams was used in the reaction. So we got this, the used in the reaction amount. Now, the starting amount for this reactant, how much was that from the original problem? Yes, it was 80. So we're going to do 80 minus the 78.93. So then we have 1.07 grams left over of N2O4. So this is using the limiting reactant to find how much of the excess was left over. That's one way. And I usually prefer this way but I sometimes use this. I prefer this way most of the time, and occasionally I use the next strategy depending upon the way the problem is set up. So the other way to do this, there's the answer, there you go. Right here is using the product amounts. And if you go back to the original problem where we solved for the water, we had the one water was like 3.431 moles. And then we had the other one was like 3.478 moles. That was from part A, where we were calculating the limiting reactant and the amount of water. What you can do is using the product amounts, you subtract these. Okay, so 3.478 minus the 3.431. And you subtract those and you get your difference in the moles. So this is doing it the product way. And sometimes this is faster than the other one, although I lean towards the other one most of the times for most problems. So we end up with moles of water left over, basically here is what we're telling. So you subtract these two, and then you start a T-chart with these moles of water that, were not produced technically, and then work it to your excess reactant. So 4 moles of water. Here's our 4 moles equals 1 mole of N2O4. And then we have 1 mole of N2O4 is 92.02 grams N2O4. And when you calculate this, I think you'll see that you get 1.08 grams of N2O4 left over. So basically they came out to being the same number, 1.07, 1.08 grams, virtually the same number. And either method can work. Now, like I said, it depends on your preference. Some people see it better this way. Some people see it better doing it the other way with the limiting reactant. And like I said, I prefer limiting reactant, but there are situations where I do like this method better, and I will use it. So you can decide, don't get anything off. Looking at example 6. This is a good example of a typical multiple choice problem where you're not allowed to use the calculator. So keep that in mind, not allowed to use the calculator here. So they give you more simplistic numbers to work with so you can do some mental math and do it quickly. All right. What you need to, go ahead and label and figure out. And a lot of this stuff you could probably do in your head. I'm going to do it all handwritten out though so everybody can see the steps. So we get 0.4 moles of the hydrogen. We have 0.15 moles of the oxygen. And then they were to react completely, what is the mass of the reactant that would remain? So you have to figure out which is limiting, what is excess. So that's my first step, is I'd just start with figuring out what's limiting, what's excess. So if I'm writing it out, I mean, some of you can just see it in your head and do this, and multiple choice questions, you don't really have to show your work. So if you can do it in your head and it goes faster for you, that's great. Going to water, I'm just going to go to moles because it's shorter and it's quicker, and I need, you know, to be faster here. So I have 2 moles of H2 going to 2 moles of water. And if you can do the mental math in your head, obviously that's going to be 0.4 moles of water. Second one, look for getting rid of your, or figuring out what your oxygen is here. There's 1 mole of oxygen to 2 moles of water. And mental math, 0.15 times 2, hopefully you can do that one in your head. That's 0.3 moles of water. Now I know this is the theoretical. This must be the what? Which one is this? The limiting? Yes, that's the limiting. Good. So guess what? I can cross these two off because they're not going to, you know, O2 is not going to remain. So those don't even need to be choices anymore, right? This is where that second method comes into play. The product one is very helpful because look, I have the products. I can subtract them. I get 0.1 moles of water. Now I can work my 0.1 moles of water to the mass of hydrogen and figure out how much is left. So 2 moles of water to 2 moles of hydrogen. 1 mole of hydrogen is 2.02 grams of hydrogen. That's off the periodic table. So moles with moles. And if you look here, you know, those cancel. So 0.1 times 2 gives you 0.20. Why my pen's not working? Grams of hydrogen. So this would be the amount left over. So obviously the answer is A. Yeah, as you can see, that's one way to do it, and you would end up getting that answer. The other way to do it takes longer, the limiting reactant one, because you could start here, you know, do 0.15 moles of O2, change that over to your hydrogen grams. So 1 mole of O2 is 2 moles of hydrogen, and then 1 mole of hydrogen is 2.02. If you do it this way, that's fine. You end up getting 0.060 grams. Now this is what was used. You still have to figure out what was starting with. So 0.40 moles of hydrogen. You have to do this one too in your head or on paper. So really you're starting with 0.08 grams. That's the starting amount. And then you would do the 0.08 minus the 0.6. You still get 0.2 grams hydrogen that's remaining, but it just, to me, it takes longer that way. I feel like this version is more efficient. Keep that in mind when you're looking at these, and remember, like on a problem like this, you don't have a calculator. You have to do it in your head. These numbers they give you are, they feel are reasonable mental math numbers to work. All right, let's look at solutions. Learning target for solutions. All I want you to be able to do is be able to use the molarity equation. Calculate moles, calculate volume, calculate molarity, calculate grams. So stuff like that about solutions. The amount of the solute in solution is given by its concentration. Concentration can be done many different ways. There's molality, there's percent by volume, percent by mass. In AP chemistry and chemistry, the general one that we use though is molarity. Does anybody remember what molarity is a measure of? Moles per liter, that's correct. So you need to know this equation. Moles per liter, okay? And be able to manipulate the variables. So molarity times liters gives you moles, and moles divided by molarity gives you liters. So be able to manipulate those variables throughout the equation. Looking at a particular model diagram here, you know, we have 1, 2, 3, 4, 5, 6, 7. Okay, 7 moles in that one. 1, 2, 3, 4, 5, 6, 7 over here. So they have the same number of solute particles in there, but what makes them different molarities? Yeah, the one on the right has more water, more liters. So the bottom part here, that number's bigger. So this one would be more dilute. The concentration would be less. Over here, this would be more concentrated. Okay, based on the fact that the volume is less there. Now, you could also adjust volume by adding more particles. You add more particles to the same volume, one would be more concentrated than the other as well. A way of manipulating, but this is a good representation of a particulate model diagram showing concentration differences. All right, so preparing a solution, you're going to use these volumetric flasks, and that's part of the lab that we're going to go over in a few minutes. The volumetric flask has a calibration mark on it. That's the line that you know where to fill the water to. Now, the key here is, of course, you're going to find the mass of how much of the solute that you need to put in. And you use a funnel, put it in, get it into the volumetric flask. And I show the procedure of this in my little lab video that you're going to see in a minute. Then you add water. Once you have the solid in the bottom, you add water just to the line. It makes making solutions a very efficient process. Volumetric flasks, you don't have to use graduated cylinders or anything because you know I put this substance in here that I calculated it to be out of 1 liter or 1,000 milliliters. And this is, when I fill it to the line, it's going to be the correct concentration. And then you just put the stopper on it or the cap on it and shake it up. So it's volumetric flasks. They expect you to know how to create a solution in a volumetric flask. So we're starting at square one with this and making sure everybody's good with it. Now in the classroom, I have ones that are 1 liter size. I have 500 milliliter ones. I have 250. I have even 100 milliliter ones that we were going to use for one of our labs. So they're various sizes. So like I don't have to make a liter of solution every time. I can make 100 milliliters if that's all I need. I just have to use the right size flask. Okay, so that's kind of the process. You'll see this more when we look at the lab paper. Example 7 is basically your basic molarity problem. And the reason why I'm going over this is because there are some in the lab and I want to make sure you can calculate these. Required to make 350 milliliters of a 0.275 molar solution. And we have copper to nitrate here. Now, using our molarity equation, you can use the molarity equation. I'm going to encourage you to use dimensional analysis instead. I'm going to show you how to do that as well. But we know the molarity because we have it right here. So we have that one. We know the milliliters, so guess what we can find? We can find the liters. So the missing component of the equation is the moles. And what can we do with moles? Always. We can change it over to mass. There you go. So this is using the equation. Before I do that though, I have to always change my milliliters to liters. So how many milliliters are in 1 liter? Yes, good. Okay, so 1,000 milliliters equals 1 liter. And for AP purposes, you do not have to show this conversion. Just move it over 3 spots. 1, 2, 3. Divide by 1,000, move it over 3. Okay, don't waste your time showing a conversion like something as simple as this. They expect that you don't have to show that. Put it in our equation, missing the moles, and then 0.3500. Now, you're going to find the moles here, and yes, just keep the raw number in your calculator. Don't round just yet. I would keep the raw number in the calculator, okay? And you can write it down. I'm just writing it down so everybody can see here. But I do need to convert this to grams because this is moles of the Cu NO32. And so I need to change that into grams at the end here because I want the mass. Now, I believe my calculations are correct. It's 187.57 grams equals 1 mole of copper to nitrate. But if somebody wants to recalculate that and make sure, go right ahead. And remember, copper to nitrate's the pretty blue stuff, the blue solutions. A lot of the copper solutions are blue. They're very pretty. And when you calculate this, you end up getting 18, I think, 0.1 grams of Cu NO32. That, I consider that to be the long way because you kind of have to stop at the mole and then do the grams to mole calculation in between. And when you're using a formula, you're always supposed to write out the formula first before substituting. So keep that in mind too on AP stuff. The more efficient way is to use this as a conversion factor. And I want you to start thinking about it as in terms of a conversion factor. That is 0.275 moles per liter. So we can set this up in our T-chart and use it. So we have 0.350 liters. Now, I can always start my T-chart with liters, mass, or moles, and then use this as a conversion factor as I'm lining up the labels and getting them to cancel. So since they gave me liters, this is what I'm going to start with. I need to find mass. Well, liters needs to go down here, so I put liters on the bottom. Well, then moles can go on the top. I insert my molarity conversion factor here. Then I can just keep going. Now the moles go down here, and I can go to grams up here. So this is the 187.57 equals 1 mole of this is the copper nitrate. So I feel like that's easier, quicker, faster. And if you calculate this, you get the 18.1 grams as well. Same thing. Okay, so start thinking about molarity and being able to use it in dimensional analysis as a conversion factor. Any questions? I'm going to show you another problem where we're going to do that as well, use the conversion factor. This one, oh yeah, there we go. There's our answer. All right, let's take a look at this one. Now we have grams, and we want to know how many liters to make the 0.65 molar solution. Okay, so this time we have the grams to start with. We want to find liters. So remember the 0.650 moles over 1 liter, we can use that as a conversion factor. The 17.5 grams, CuNO32. And I just did that calculation for the molar mass. It's 187.57 grams, so I don't have to redo that. That equals 1 mole. Now I can go use my conversion factor up here. Now, moles though, the moles are going to go down here, and the liters are going to go on the top. So I'm going to flip it. So I get 0.650 moles equals 1 liter. Now everything's going to cancel correctly, and I'm going to end up with my liters, which is what I want. So just an example of also using it as the molarity as the conversion factor as you're calculating. Now, if you have to stick with the equation for now, that's okay. We're going to do much more practice with this when we get to Unit 3. But I wanted to show you now so you have an idea of how to do it. If you want to use it. You can use the equation too, that's fine. So this ends up being, I think, 0.144 liters